Hello there, and welcome to the Sleepy Astronaut, where cosmic mysteries drift gently through the darkness and science unfolds like a quiet constellation above your pillow. Tonight's gentle voyage takes us beyond the familiar borders of our solar system to witness something that has never happened before in recorded history, the collision between a visitor from another star and the sun's most violent outburst. It's a story written in plasma and ice, in ancient starlight and magnetic fury. But before we embark on this interstellar adventure, I'd love to know, where in the cosmos are you listening from tonight? And what time is it in your corner of Earth? Fitting, isn't it? A video about celestial encounters, and here we are, scattered across time zones, each finding this moment under the same vast sky that holds our mysterious visitor. If this cosmic journey brings you peace, wonder, or simply a soothing way to drift toward dreams, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little sanctuary of space science reach other stargazers who might need a gentle pause beneath the night sky. Now, I do hope the wonders ahead don't keep you too captivated to sleep. But if they do, well, at least you'll dream of distant suns and wandering worlds. So settle in, let your thoughts slow like distant orbits, and let's begin, because somewhere between the silence of deep space and the fury of solar storms lies the extraordinary tale of 3I/ATLAS. Imagine, if you will, a traveller that has journeyed for billions of years across the vast emptiness between stars, drifting through the cosmic dark, long before Earth had formed its first oceans, long before the sun had settled into its steady rhythm. This wanderer carries within its icy heart the secrets of another stellar system, the fingerprints of alien suns, and the chemical whispers of worlds we may never see. And then, after eons of silent travel through the galactic night, it enters our solar neighborhood just as our own star decides to unleash one of its most spectacular tantrums. This is the story of 3I/ATLAS, the third confirmed interstellar object to grace our solar system, and the unprecedented moment when it collided with a coronal mass ejection from our sun. On a quiet morning in July 2025, astronomers at the Atlas telescope station in Rio Hurtado, Chile, were scanning the heavens when they spotted something unusual moving against the background stars. At first, it appeared to be just another faint dot among millions. But as they tracked its motion over several nights, something remarkable became clear. This object was moving far too fast to belong to our solar system. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. It was passing through like a cosmic tourist on the journey of a lifetime. They named it 3I/ATLAS, the third interstellar object we have ever identified. And immediately it began revealing secrets that challenged everything astronomers thought they knew about visitors from other stars. To understand just how extraordinary this discovery is, we must first appreciate the rarity of such encounters. Our solar system is a tiny island in an ocean of space, surrounded by the nearest stars at distances so vast that light itself takes years to bridge the gaps between them. For an object to escape one star system, travel through this cosmic desert, and happen to pass close enough to another star for us to detect it, requires a convergence of circumstances so unlikely that it borders on miraculous. And yet here was 3I/ATLAS, racing through our inner solar system at the staggering speed of 210,000 kilometers per hour, the fastest velocity ever recorded for any object visiting our cosmic neighborhood. But 3I/ATLAS was different from its predecessors in ways that immediately captured scientific attention. The first interstellar visitor, 1I/Oumuamua, discovered in 2017, was a mysterious, elongated object about the size of a football field that tumbled through space without showing any signs of the typical comet behavior. Astronomers expected its strange acceleration and lack of a visible tail spark debates that continue to this day, with some scientists proposing explanations ranging from unusual outgassing to more exotic possibilities the second visitor. 2I/Borisov, discovered in 2019, behaved much more like a traditional comet, developing a beautiful tail as it approached the Sun, and reassuring astronomers that at least some interstellar objects conform to expectations. 3I/ATLAS, however, dwarfed both of its predecessors in sheer scale. Early estimates suggested it might span anywhere from 5 to 20 kilometers across, making it potentially thousands of times more massive than Oumuamua. This enormous size difference raised profound questions about the object's origins and composition. Most interstellar objects are expected to be relatively small fragments ejected during the chaotic early formation of planetary systems. But 3I/ATLAS appeared to be something far more substantial, perhaps a remnant from the outer reaches of its parent system, where giant planets might have hurled it into the cosmic void. As 3I/ATLAS continued its inbound journey toward the Sun, astronomers around the world trained their most powerful instruments on this visitor from the stars. The Hubble Space Telescope captured detailed images that revealed an active nucleus surrounded by a growing atmosphere of gas and dust. The James Webb Space Telescope analyzed its composition and found it unusually rich in carbon dioxide, suggesting a chemical makeup that might differ significantly from comets born in our own solar system. These observations painted a picture of an object that had preserved within its frozen interior a chemical snapshot of its distant birthplace. But perhaps the most intriguing aspect of 3I/ATLAS was not just its size or composition, but the timing of its arrival. Unlike Oumuamua, which was discovered after it had already rounded the Sun and was heading back toward interstellar space, 3I/ATLAS was spotted well before its closest approach. This gave astronomers an unprecedented opportunity to observe an interstellar object throughout its entire passage through our inner solar system, from its first detection in the outer reaches to its eventual departure back into the cosmic dark. As summer turned to autumn in 2025, 3I/ATLAS continued its relentless approach toward the Sun, growing brighter as solar radiation began to heat its ancient surface and release gases that had been frozen for billions of years. The comet developed a characteristic greenish glow as diatomic carbon molecules energized by ultraviolet radiation began to fluoresce like cosmic fireflies. Astronomers watched with fascination as this visitor from another star began to awaken from its long slumber in the space between worlds. Meanwhile, 93 million miles away, our Sun was entering a period of heightened activity. Solar cycle 25 was reaching toward its peak, bringing with it an increase in solar flares, coronal mass ejections, and other manifestations of our star's magnetic fury. The Sun's corona, that ethereal outer atmosphere visible during total eclipses, was becoming increasingly unstable as magnetic field lines twisted and tangled under the pressure of the solar dynamo deep within the Sun's core. Coronal mass ejections represent some of the most powerful explosions in our solar system. Imagine 1 billion tons of plasma superheated gas so hot that atoms are stripped of their electrons, hurled into space at speeds that can exceed 1,000 kilometers per second. These events begin when the Sun's magnetic field lines become so twisted and stressed that they suddenly snap and reconnect, releasing enormous amounts of stored magnetic energy in a fraction of a second. The result is a bubble of magnetized plasma that expands outward from the Sun, like a cosmic shockwave, carrying with it the power to disrupt satellite communications, trigger auroras, and in extreme cases, even damage power grids on Earth. On a seemingly ordinary day in late August 2025, one such coronal mass ejection erupted from the Sun's surface, aimed directly along the path where 3I/ATLAS was traveling. This was not targeted. Of course, the Sun has no awareness of the interstellar visitor approaching through its domain. But the timing was extraordinary. a cosmic coincidence that would create an encounter never before witnessed in the history of astronomy. The coronal mass ejection raced outward from the Sun at tremendous speed, carrying with it a magnetic field strong enough to deflect cosmic rays and a density of charged particles millions of times greater than the normal solar wind. As news of this impending collision spread through the astronomical community, telescopes around the world and in space began turning toward the expected point of impact. Scientists had observed coronal mass ejections striking comets before, most famously, in 2007, when the STEREO spacecraft watched as a CME completely severed the tail of Comet Encke. But those were comets born in our own solar system, objects whose compositions and behaviors were at least somewhat familiar. 3I/ATLAS represented something entirely different. A messenger from another star carrying within its nucleus the secrets of an alien world, the physics of what happens when a coronal mass ejection encounters a comet are both beautiful and violent. As the high-speed plasma cloud approaches the comet, it begins to interact with the thin atmosphere of gas and dust surrounding the nucleus. The comet's own weak magnetic field, if it has one, becomes entangled with the much stronger magnetic field carried by the coronal mass ejection. This interaction can strip away portions of the comet's tail, twist its coma into spectacular spirals, and even affect the rate at which the nucleus releases gas and dust. But 3I/ATLAS was not just any comet. It was an interstellar wanderer whose composition might be fundamentally different from anything in our solar system, forged in the outer reaches of another star system, under conditions that might have been vastly different from those that created the comets in our own Kuiper belt and Oort cloud. Would it respond to the Sun's assault in the same way as its solar system cousins? Or would this collision reveal new physics, new chemistry, new insights into the nature of worlds beyond our cosmic neighborhood? The encounter promised to be a natural laboratory for studying the interaction between solar activity and interstellar matter. On a scale never before possible, astronomers prepared their instruments and waited, knowing they were about to witness something that might not occur again for centuries. The collision between a visitor from the stars and the fury of our own sun was about to unfold in the theater of space, where the only audience would be the telescopes of Earth and the infinite silence of the cosmos. When the collision finally occurred, it unfolded with a grace that belied the tremendous forces at play. The coronal mass ejection reached 3I/ATLAS like a ghostly tide of magnetized plasma, washing over the comet in a display that would have been invisible to the naked eye, but blazed brilliantly in the specialized instruments trained upon it from Earth. The interaction began subtly at first as the leading edge of the solar storm encountered the outermost wisps of the comet's atmosphere. But within hours, the full fury of the sun's eruption engulfed the interstellar visitor in a cocoon of charged particles and twisted magnetic fields. What astronomers witnessed challenged their expectations in ways both subtle and profound, unlike the dramatic tail severance they had observed with solar system comets. 3I/ATLAS seemed to absorb the coronal mass ejection's impact with remarkable resilience. Its massive nucleus, estimated to weigh over 30 billion tons, provided an anchor of stability that smaller comets might have lacked. While the plasma storm raged around it, the comet's tail did not simply vanish, but instead underwent a complex transformation, stretching and contorting as magnetic field lines wrapped around it like invisible ribbons in a cosmic wind. The spectacle revealed itself most clearly in the radio frequencies, where the interaction between solar plasma and cometary gas creates a symphony of electromagnetic emissions that tell the story of collision and chemistry. Radio telescopes around the world detected bursts of activity as the two very different magnetic environments merged and separated in a dance of attraction and repulsion. The signals painted a picture of turbulence on scales both vast and intimate, as particles accelerated to tremendous speeds and magnetic fields reconnected in brilliant flashes of energy. Perhaps most intriguingly, The encounter seemed to trigger changes in 3I/ATLAS itself that persisted long after the coronal mass ejection had swept past the comet's rate of gas production, which had been steadily increasing as it approached. The Sun suddenly surged to levels far higher than models had predicted it was, as if the solar storm had awakened something deep within the ancient nuclear-stirring reservoirs of volatile materials that had remained dormant for billions of years. The chemistry of this awakening told a story written in spectral lines and molecular signatures that spoke of the alien conditions under which this wanderer had formed. Spectroscopic analysis revealed that the gases now streaming from 3I/ATLAS carried isotopic ratios. Unlike anything found in our solar system's comets, the proportion of heavy water to normal water, the abundance of certain carbon compounds, the presence of trace elements that hinted at formation processes under a different star, all painted a picture of truly alien origins. Astronomers found themselves reading the chemical autobiography of another world encoded in the light of molecules, excited by solar radiation and freed from their icy prison by the fury of our sun. But the story of 3I/ATLAS was far from over as autumn progressed and the comet continued its approach toward its closest point to the Sun. Scientists realized they were witnessing something unprecedented in the annals of astronomy. The collision with the coronal mass ejection had not merely been a spectacular light show, but had fundamentally altered the visitor's behavior in ways that would provide insights into both solar physics and the nature of interstellar objects for years to come. The enhanced activity triggered by the solar storm created a natural experiment in cometary evolution compressed into a time frame that would normally take months or years to unfold, as 3I/ATLAS approached its perihelion. The point of closest approach to the Sun, its nucleus began to reveal internal structures that had been hidden beneath layers of ancient ice radar observations, suggested a complex interior, possibly differentiated with denser materials toward the center and lighter ices forming an outer shell. This was not the simple dirty snowball that early comet models had proposed, but something far more sophisticated, a remnant of planetary formation processes in another star system. The gravitational influence of our Sun also began to reveal secrets about where 3I/ATLAS had come from. By carefully tracking its trajectory and working backward through galactic motions, astronomers could trace the comet's path through space over millions of years. The calculations suggested it had originated from the thick disk of our galaxy, an older region populated by stars with different chemical compositions than our own Sun. This ancient heritage was written in every molecule released by the comet's warming nucleus. A library of cosmic history dating back to when the galaxy itself was younger and the processes of star and planet formation were still learning their rhythms. As 3I/ATLAS continued its solar approach, the international community of astronomers coordinated the most comprehensive observation campaign ever mounted for an interstellar object space. Base telescopes tracked its every movement, while ground-based observatories captured spectra that revealed the chemical fingerprints of an alien world. Radio dishes listened for the whispers of magnetic field interactions, and particle detectors measured the subtle ways the comet influenced the solar wind flowing around it. The visitor's influence extended far beyond its immediate vicinity, as 3I/ATLAS traveled through the inner solar system. It left a wake of disturbed space weather that could be detected by satellites monitoring the solar wind. The comet acted like a stone thrown into the smooth flow of particles streaming from the Sun, creating ripples and eddies that propagated outward at the speed of sound in the plasma medium. These disturbances provided a natural probe of conditions in the solar wind, allowing scientists to study the Sun's extended atmosphere with unprecedented detail. Meanwhile, the comet's own magnetic environment began to reveal itself as a complex and dynamic system, unlike the simple dipole fields of planets 3I/ATLAS seemed to generate a chaotic patchwork of magnetic domains that shifted and evolved as different regions of its nucleus heated and released gas. The interaction between these local magnetic fields and the solar wind created miniature versions of the same processes that generate Earth's auroras, but on scales both smaller and stranger. The implications of these observations extended far beyond the immediate fascination of watching an interstellar visitor navigate our solar system. For the first time, scientists had direct evidence of how objects from other star systems behave when exposed to our sun's radiation and magnetic field. The data would inform models of planetary formation throughout the galaxy and provide insights into the processes that eject comets and asteroids from their birth systems to wander the cosmic dark. As winter approached and 3I/ATLAS continued its relentless journey toward the sun, the comet began to display behaviors that defied easy explanation. Its brightness fluctuated in complex patterns that suggested a nucleus with an irregular shape rotating in a tumbling motion that sent different faces toward the sun. In an ever-changing sequence, the spectral signatures of its coma. The envelope of gas and dust surrounding the nucleus showed variations that hinted at regional differences in composition across the surface. Some areas seemed rich in water ice, while others showed concentrations of carbon dioxide or more exotic compounds. These variations painted a picture of a world that had experienced a complex history before its ejection into interstellar space. Perhaps 3I/ATLAS had formed in the outer reaches of its parent system, where different temperature and pressure conditions led to the segregation of various ices. Or perhaps it was a fragment of a larger body that had been shattered by gravitational forces or collisions, leaving behind a remnant that carried within itself the chemical signatures of multiple formation environments. The mystery deepened as observations revealed that 3I/ATLAS was not simply a passive victim of solar heating, but seemed to respond to the sun's influence in ways that suggested internal structure and dynamics. The comet's activity did not follow the smooth curves that models predicted for a homogeneous nucleus, but instead showed sudden surges and lulls that hinted at the exposure of fresh material or the exhaustion of volatile deposits in specific regions. These outbursts created temporary changes in the comet's appearance as jets of gas and dust erupted from active areas on the nucleus, creating streamers and fans that evolved over hours or days. The choreography of these eruptions followed no earthly rhythm. Instead, they seemed to dance to the alien music of a world born under foreign stars. Each jet told a story of subsurface processes that had been dormant for eons, awakening now under the gentle but persistent caress of solar radiation. As 3I/ATLAS wheeled through space, these fountains of ancient ice painted temporary brushstrokes across the cosmic canvas, visible to telescopes as ephemeral beauty marks on the face of the interstellar wanderer. Scientists watching this display began to realize they were witnessing something that challenged fundamental assumptions about how comets behave. The traditional models assumed that comet nuclei were relatively uniform balls of ice and rock that heated and cooled predictably as they approached and receded from the sun. But 3I/ATLAS seemed to possess an internal architecture that governed its responses to solar heating in ways that spoke of complexity far beyond the simple dirty snowball hypothesis. Deep within the comet's nucleus, layers of different materials told the story of its formation in an alien solar system. Some regions were dominated by water ice, the familiar compound that makes up Earth's oceans, but frozen under conditions so cold that it had remained solid for billions of years. Other areas showed concentrations of carbon dioxide ice and methane compounds that formed under the frigid conditions of the outer reaches, where giant planets shepherd their retinues of icy debris. The chemical gradients within the nucleus created a kind of archaeological record of the temperature and pressure conditions that existed when this world first condensed from the primordial disk around its parent star. As the months passed and 3I/ATLAS drew ever closer to its appointment with the Sun, these internal differences began to express themselves in increasingly dramatic ways. The water ice regions activated first as they required less energy to sublimate directly from solid to gas, creating the initial atmosphere that had first announced the comet's presence to astronomers on Earth. But as solar heating penetrated deeper into the nucleus, it began to reach deposits of more volatile materials that had remained frozen at temperatures where water ice was already active. The result was a series of explosive events that sent plumes of gas and dust streaming away from the comet at velocities that surprised observers. These were not the gentle, steady outgassing that characterizes most comets, but violent eruptions that spoke of pressure building up beneath insulating layers of less volatile material until the accumulated stress overcame the structural integrity of the overlying ice. The sudden release created geysers of alien chemistry that painted themselves across the sky in wavelengths invisible to human eyes, but blazingly obvious to the sensitive detectors of modern astronomy. Each eruption was like opening a time capsule from another world. The gases that escaped carried with them isotopic signatures that revealed the stellar environment where 3I/ATLAS had formed the ratio of different forms of hydrogen, oxygen, and carbon told stories of nuclear processes in a star that might have been quite different from our own sun, perhaps older, perhaps more massive, perhaps surrounded by planetary disks, with chemical compositions that reflected different initial conditions in their stellar nursery. The detective work required to decode these chemical messages pushed the boundaries of astronomical spectroscopy. Scientists found themselves developing new techniques to extract meaning from the faint light scattered by molecules that had never before been observed in such detail. The spectrum of 3I/ATLAS became a Rosetta Stone for understanding the chemistry of world formation around other stars. Each absorption line a clue to conditions that existed in a place and time so distant that light itself had not yet had time to carry news of that world to Earth. But the scientific treasure trove was not limited to chemistry alone. The physical behavior of 3I/ATLAS, as it responded to solar heating, provided insights into the mechanical properties of materials formed under alien conditions, the way the comet's surface cracked and sublimated the patterns of dust emission, the rotation changes induced by asymmetric outgassing. All painted a picture of a world with material properties that reflected its exotic origins. The gravitational field measurements made possible by careful tracking of the comet's trajectory revealed internal density variations that hinted at a complex structure. Perhaps 3I/ATLAS was not a single coherent body, but rather an assemblage of fragments held together by their mutual gravitational attraction. A rubble pile of alien debris that had somehow survived the violent ejection from its parent system and the long journey through interstellar space. This possibility raised intriguing questions about the processes that create interstellar wanderers and the kinds of disruptions that can send entire worlds into exile among the stars. As winter deepened and 3I/ATLAS approached the final phase of its inbound journey, the comet's behavior became increasingly erratic and spectacular. The combination of intense solar heating and the lingering effects of its encounter with the coronal mass. Ejection had awakened processes within the nucleus that created a constantly changing display of jets, fountains, and expanding clouds of debris. The comet had become a natural laboratory for studying the physics of sublimation under extreme conditions, providing data that would inform models of similar processes throughout the galaxy. The tale of 3I/ATLAS had grown to span millions of kilometers, a gossamer thread of dust and gas that caught and scattered sunlight in ways that revealed the complex interplay between solar radiation pressure and the comet's own gravity. The tail was not a simple streamer pointing away from the sun, but a complex structure with multiple components, each responding differently to the various forces acting upon it. The dust tail followed the classic curved path dictated by solar radiation pressure, while the gas tail aligned more closely with the solar wind, creating a bifurcated structure that spoke of the different physics governing particles of different sizes and compositions. Within this tail, astronomers detected signatures of materials that had no earthly counterpart minerals, that had condensed under pressure and temperature conditions impossible to replicate in terrestrial laboratories. The spectroscopic analysis revealed crystal structures and molecular arrangements that provided direct evidence of the exotic environments that exist in the outer reaches of other stellar systems, where the chemistry of world formation follows pathways unknown in our own cosmic neighborhood. The electromagnetic environment around 3I/ATLAS had also evolved into something unprecedented. The comet's interaction with the solar wind had created a complex magnetic structure that extended far beyond the visible nucleus-charged particles streaming from the sun, became trapped in magnetic field lines generated by the comet's own electrical activity, creating a kind of miniature magnetosphere that pulsed and fluctuated with the rhythm of solar activity. Radio telescopes detected emissions from this magnetic environment that told stories of particle acceleration and electromagnetic reconnection on scales, both intimate and vast. The comet had become a natural particle accelerator, creating high-energy electrons and ions that spiraled along magnetic field lines and emitted characteristic radiation signatures. These signals provided a window into fundamental plasma physics processes that occur throughout the galaxy wherever magnetic fields and charged particles interact under extreme conditions. As 3I/ATLAS continued its approach toward perihelion, the point of closest solar approach scheduled for late October, the anticipation within the astronomical community reached fever pitch. Never before had scientists had the opportunity to observe an interstellar object throughout such a complete orbital phase, from initial detection through maximum activity and eventual recession back toward the cosmic dark. The data being collected would provide insights into interstellar chemistry, physics, and dynamics that would inform theories of planetary system formation for decades to come. The comet's influence had also begun to extend beyond the immediate scientific community as news of the spectacular collision with the solar storm and the ongoing display of alien chemistry reached the public imagination. 3I/ATLAS became a symbol of the vast unknown that surrounds our small world, a reminder that we live in a galaxy populated by countless worlds, whose stories we are only beginning to read in the faint light of their wandering messengers. Amateur astronomers around the world trained their telescopes on the brightening comet, contributing observations that helped professional scientists track the rapidly evolving changes in its appearance and behavior. The collaborative effort created a global network of observers united in their fascination with this visitor from the stars, whose journey had brought it into temporary communion with our own solar family. But perhaps most remarkably, 3I/ATLAS had begun to reveal that the galaxy is far more interconnected than anyone had previously imagined. The chemical signatures detected in its outgassing showed clear relationships to stellar nucleosynthesis processes that had occurred billions of years ago in stars that had lived and died long before our own sun was born. The comet carried within its frozen heart a record of galactic chemical evolution that spanned eons, telling the story of how the elements that make up planets and life itself had been forged in stellar furnaces and distributed through space by the explosive deaths of massive stars. The isotopic ratios found in the comet's emissions provided direct evidence of these ancient processes, showing how successive generations of stars had enriched the galaxy with heavier elements through the endless cycle of stellar birth, death and rebirth. 3I/ATLAS was not just a visitor from another star system, but a messenger from the deep past, carrying news of cosmic processes that had shaped the chemical foundation upon which all subsequent world formation would build. As the comet continued its relentless approach toward the sun, These revelations painted an ever more detailed picture of a universe far richer and more complex than human imagination had dared to envision. Each new observation added another piece to the cosmic puzzle, revealing connections and relationships that spanned both space and time on scales that challenged comprehension, yet filled the heart with wonder at the magnificent choreography of creation that plays out in the darkness between the stars. The revelation that 3I/ATLAS carried within its ancient nucleus the chemical fingerprints of stellar generations long dead transformed our understanding of what interstellar objects truly represent. They are not merely cosmic debris wandering aimlessly through the void, but rather time capsules that preserve the history of galactic evolution in frozen libraries of ice and rock. Each molecule released by the warming comet told a story that stretched back to the very foundations of heavy element formation in the universe, when the first massive stars ended their brief lives in spectacular explosions that seeded space with the building blocks of worlds. As October approached, and 3I/ATLAS drew within striking distance of its perihelion, the comet's behavior entered a new phase of complexity that challenged every model astronomers had developed for cometary activity. The nucleus began to exhibit what could only be described as seasonal changes, despite the fact that its day lasted mere hours rather than months or years. Different regions of the surface seemed to activate and deactivate in patterns that suggested an internal structure far more sophisticated than anyone had anticipated. The northern hemisphere of the nucleus, if such terrestrial terms could be applied to this alien world, showed a predominance of water ice sublimation that created steady, predictable jets of vapor and dust. But the southern regions told a different story entirely, dominated by more exotic ices that required higher temperatures to activate. As the comet's rotation brought these southern territories into fuller sunlight, they erupted with sudden violence that sent shockwaves through the surrounding coma and created temporary disruptions in the tail structure that could be observed from Earth in real time. These regional differences painted a picture of a world that had experienced a complex thermal history during its formation. Perhaps 3I/ATLAS had originally formed in the outer reaches of its parent system, where temperatures were so low that even carbon dioxide remained frozen, only to be perturbed inward by gravitational interactions that exposed different regions to varying degrees of stellar heating before its final ejection into interstellar space. The resulting chemical zonation created a kind of geological map written in ice, with each region preserving the conditions that existed when it last equilibrated with its environment billions of years ago. The gravitational perturbations caused by these asymmetric eruptions began to have measurable effects on the comet's trajectory and rotation state. 3I/ATLAS was not simply falling passively toward the Sun, but was actively steering itself through space, as the reaction forces from its jets created tiny but persistent changes in velocity. These non-gravitational accelerations, as astronomers termed them, provided yet another window into the internal processes governing the comet's behavior. By carefully measuring these trajectory changes and correlating them with observations of outgassing activity, scientists could map the locations and orientations of active regions on the nucleus with remarkable precision. The resulting picture showed a world covered in a patchwork of different terrains, each with its own thermal properties and volatile content. Some areas appeared to be covered with a dark, non-volatile lag deposit that insulated the underlying ice from solar heating, while others showed exposed patches of nearly pure ice that responded dramatically to even small increases in temperature. The thermal modeling required to understand these processes pushed computational techniques to their limits. The traditional approaches that worked well for solar system comets, which formed under relatively uniform conditions and followed predictable orbital patterns, proved inadequate for describing the behavior of this interstellar wanderer. New algorithms had to be developed that could account for the exotic chemical compositions and the complex thermal history that 3I/ATLAS had experienced during its journey through the galaxy. As the comet's activity intensified, ground-based observatories began to detect phenomena that had never been seen before in any celestial object. High-resolution spectroscopy revealed molecular species that existed only transiently in the coma, complex organic compounds that formed through chemical reactions between simpler molecules in the low-density environment surrounding the nucleus. These reactions were driven by solar ultraviolet radiation and occurred at temperatures and pressures impossible to achieve in terrestrial laboratories. The discovery of these exotic molecular species opened an entirely new field of astrochemistry focused on understanding the chemical evolution of materials in the unique environment of a cometary coma. The processes occurring around 3I/ATLAS provided a natural laboratory for studying reaction pathways that might be common throughout the galaxy wherever similar conditions exist. The implications extended far beyond cometary science to questions about the chemical foundations of life itself and the pathways through which complex organic molecules might form in space. Radio observations revealed that the electromagnetic environment around 3I/ATLAS had evolved into something resembling a miniature version of planetary magnetospheres. The comet's interaction with the solar wind had created bow shocks and magnetic field draping effects that accelerated charged particles to high energies and generated radio emissions detectable across vast distances. These signals carried information about the fundamental plasma physics processes that govern interactions between stellar winds and small bodies throughout the galaxy. The magnetic field measurements also revealed something unexpected about the comet's internal structure. Unlike the weak and chaotic magnetic fields typically associated with small solar system bodies, 3I/ATLAS seemed to possess organized magnetic domains that suggested either a partially differentiated interior or perhaps the remnants of an ancient magnetic field frozen into the nucleus during its formation. This possibility raised intriguing questions about the magnetic environments that existed in the early stages of its parent planetary system. As the comet continued its approach, the solar wind monitoring satellites positioned throughout the inner solar system began to detect the wake that 3I/ATLAS left in the interplanetary medium. The comet was not simply moving through empty space, but was ploughing through the tenuous but measurable density of particles streaming from the Sun. This interaction created disturbances that propagated both upstream and downstream from the comet's position, forming a kind of electromagnetic signature that could be detected by sensitive instruments millions of kilometers away. The wake structure revealed details about the comet's mass and cross-sectional area that complemented the optical observations of its nucleus. By measuring how the solar wind flow was deflected around the obstacle presented by the comet and its extended coma, scientists could infer properties of the nucleus that were not directly observable. The results suggested that 3I/ATLAS possessed a density intermediate between pure ice and solid rock, consistent with a composition that included significant amounts of both volatile and refractory materials. The approach to perihelion also provided an opportunity to test theories about how interstellar objects might behave under extreme thermal stress. Some models predicted that the rapid heating experienced near the Sun might cause structural failure in objects that had been exposed to the temperature cycling of interstellar space for billions of years. The thermal shock of transitioning from the cosmic background temperature of just a few degrees above absolute zero to the intense heating near the Sun might be sufficient to fracture even large nuclei. But 3I/ATLAS seemed to be weathering this thermal assault with remarkable resilience. While its activity had increased dramatically and regional variations in outgassing created spectacular displays of jets and fountains, the nucleus appeared to remain structurally intact. High-resolution imaging revealed surface features that persisted from one observation to the next, suggesting that whatever processes had shaped the comet's exterior during its interstellar journey had created a surface strong enough to withstand the stresses of solar approach. The dust analysis conducted by space-based telescopes revealed another layer of complexity in the comet's composition. The particles streaming away from the nucleus showed a wide range of sizes and compositions, from microscopic grains of silicate minerals to larger chunks of what appeared to be organic compounds. The size distribution of this dust provided clues about the processes that had originally assembled the comet's nucleus and the mechanisms by which material was now being released. Some of the dust grains showed evidence of having been processed by high-energy radiation during the comet's journey through interstellar space. Cosmic rays, the high-energy particles that permeate the galaxy, had gradually altered the crystal structure and chemical composition of surface materials over the billions of years of the comet's wandering. These radiation effects created a kind of chronometer that could be used to estimate how long 3 I/ATLAS had been traveling through the void. The isotopic analysis of this processed dust revealed signatures of neutron capture reactions that could only have occurred under bombardment by cosmic rays over geological timescales. The degree of alteration provided direct evidence that the comet had indeed spent billions of years in interstellar space, confirming the trajectory calculations that traced its origin back to the thick disk of the galaxy where older stellar populations reside. As 3 I/ATLAS approached within 2 astronomical units of the Sun, roughly twice the distance of Earth's orbit, the comet's brightness had increased to the point where it became visible to dedicated amateur astronomers using modest telescopes. This accessibility to ground-based observers created an unprecedented opportunity for citizen science participation in the study of an interstellar object. Astronomy clubs and educational institutions around the world organized observing campaigns that contributed valuable data to the professional research effort. The collaborative observations revealed that the comet's activity showed variations on multiple timescales, from rapid fluctuations that occurred over minutes to longer-term trends that played out over weeks. These temporal variations provided insights into the physical processes governing outgassing and the three-dimensional structure of the nucleus. By correlating observations made simultaneously from different longitudes on Earth, astronomers could reconstruct the geometry of active regions and track how they evolved as different parts of the nucleus were exposed to solar heating. The public engagement generated by 3 I/ATLAS also highlighted the broader significance of interstellar object research for understanding our place in the galaxy. Here was tangible evidence that planetary systems throughout the Milky Way were connected by the exchange of material ejected during their formation and evolution. The discovery that such objects carry chemical signatures of their origins meant that each interstellar visitor was potentially a probe sent from distant worlds, carrying news of conditions and processes occurring light years away. The philosophical implications of this realization began to permeate discussions both within the scientific community and in popular culture. If 3 I/ATLAS could travel from its birth system to ours, then presumably objects from our own solar system were also wandering through the galaxy, potentially carrying Earth's chemical signature to other star systems. The possibility that life itself might spread between worlds through such natural panspermia mechanisms added an additional layer of significance to the study of interstellar objects. As the final weeks before perihelion approached, the intensity of observations reached a crescendo that taxed the capabilities of observatories worldwide. Every major telescope, both ground-based and spaceborne, had been allocated time to study different aspects of the comet's behavior during its closest approach to the Sun. The coordination required to optimize this observational campaign represented one of the largest collaborative efforts in the history of astronomy. The data flowing in from this global network of instruments painted an ever more detailed picture of processes occurring on scales ranging from the microscopic to the astronomical. Individual molecules could be tracked as they sublimated from the nucleus and underwent chemical evolution in the coma, while simultaneously the comet's gravitational influence on the solar wind could be monitored across volumes of space larger than Earth's orbit. The symphony of data streaming from telescopes around the world began to reveal that 3I/ATLAS was approaching a critical threshold in its solar encounter. As the comet drew closer to its October rendezvous with perihelion, the intensity of solar radiation bathing its ancient surface increased exponentially, triggering cascading changes that transformed the visitor from a distant speck of light into one of the most active objects in the inner solar system. The transformation was not gradual, but seemed to occur in sudden jumps as different temperature thresholds were crossed and new reservoirs of volatile materials were exposed to the sun's relentless energy. The thermal modeling teams working around the clock to predict the comet's behavior found themselves constantly revising their calculations as 3I/ATLAS continued to surprise them with its responses to solar heating. Traditional models assumed that comets heated smoothly and predictably as they approached the sun. But this interstellar wanderer seemed to possess internal structures that created feedback loops and non-linear responses to temperature changes. Regions of the nucleus that had remained dormant for weeks would suddenly burst into activity, while other areas that had been vigorously outgassing would just as mysteriously fall silent. These behavioral patterns suggested that the comet's nucleus was not a homogeneous mixture of ice and rock, but rather a complex assemblage of distinct terrains, each with its own thermal history and volatile inventory. Some regions appeared to be mantled with dark, organic-rich material that absorbed solar energy efficiently, but conducted heat poorly, creating insulating layers that protected underlying ices until critical temperatures were reached. When these thermal barriers were finally breached, the sudden exposure of fresh ice created explosive outbursts that sent jets of material streaming away from the nucleus at velocities approaching the speed of sound. The spectroscopic signatures of these jets revealed chemical compositions that varied dramatically depending on which region of the nucleus was active at any given time. Some eruptions were dominated by water vapor, the familiar signature of heating ice, but others showed exotic cocktails of carbon monoxide, methane, and more complex organic molecules that spoke of formation conditions, unlike anything found in our solar system's reservoir of comets. The diversity of these chemical signatures painted a picture of a world that had experienced multiple episodes of heating and cooling during its formation, each leaving behind distinct layers in the nucleus like geological strata in terrestrial rocks. The gravitational perturbations caused by these asymmetric outbursts had begun to accumulate into measurable changes in the comet's trajectory and spin state. 3I/ATLAS was not simply falling toward the sun under the influence of gravity, but was actively maneuvering through space as the rocket-like thrust from its jets pushed and pulled it in directions determined by the orientation and intensity of active regions on the nucleus. These non-gravitational forces were subtle but persistent, creating trajectory changes that could be detected by careful analysis of the comet's position relative to background stars. By correlating the timing and direction of these trajectory changes with observations of outgassing activity, astronomers could map the three-dimensional structure of active regions on the nucleus with remarkable precision. The resulting picture showed a world covered in a complex patchwork of terrains, some smooth and relatively uniform, others rough and heavily cratered, still others showing evidence of past episodes of violent activity that had carved valleys and ridges into the surface. The geological diversity was astonishing for an object that had spent billions of years in the uniform cold of interstellar space. The magnetic field measurements being conducted by solar wind monitoring spacecraft throughout the inner solar system revealed that 3I/ATLAS was creating disturbances in the interplanetary medium that extended far beyond its visible coma. The comet's interaction with the solar wind had generated a bow shock structure similar to those found around planets, but scaled to the much smaller size and weaker gravitational field of the comet nucleus. This miniature magnetosphere was constantly evolving as the solar wind conditions changed and as different regions of the comet became active or dormant. Within this magnetic environment, Charged particles were being accelerated to high energies through processes that created radio emissions detectable by sensitive receivers on Earth. The radio spectrum of 3I/ATLAS had become a complex symphony of signals that revealed the physics of particle acceleration and magnetic reconnection occurring in the space around the comet. These processes were similar to those that generate the spectacular auroral displays in Earth's polar regions, but occurring in an environment with vastly different parameters of density, temperature, and magnetic field strength. The dust analysis being conducted by space-based infrared telescopes revealed another dimension of the comet's complexity. The particles streaming away from the nucleus showed evidence of having undergone significant processing during their residence in the comet's interior. Some grains appeared to be pristine condensates from the original protoplanetary disk around the comet's parent star, preserving chemical and isotopic signatures from the epoch of planetary formation. Others showed clear evidence of alteration by cosmic ray bombardment during the long journey through interstellar space, creating new mineral phases and isotopic anomalies that served as chronometers of the comet's wandering. The size distribution of dust particles also told a story of the physical processes governing the comet's disintegration under solar heating. The smallest grains were lifted away from the nucleus by radiation pressure and entrained in the gas flow created by sublimating ices, while larger particles followed more complex trajectories determined by the balance between solar radiation pressure, gas drag, and the weak gravitational field of the nucleus. The resulting dust environment around 3I/ATLAS created a kind of natural particle accelerator that provided insights into fundamental physics processes occurring under conditions impossible to replicate in terrestrial laboratories. As the comet's brightness continued to increase and its tail grew to span tens of millions of kilometers, ground-based observers began to detect phenomena that challenged their understanding of cometary physics. High-resolution imaging revealed structures within the tail that appeared to be organized into discrete filaments and knots, suggesting that the outflow from the nucleus was not uniform, but was channeled by magnetic fields and pressure gradients in ways that created complex three-dimensional geometries. The spectroscopic analysis of different regions within the tail revealed chemical gradients that provided insights into the evolution of material as it traveled away from the nucleus. Molecules that were stable near the comet underwent photodissociation and ionization as they moved into regions of more intense solar ultraviolet radiation, creating daughter products that fluoresced at characteristic wavelengths. The spatial distribution of these emission lines created a kind of chemical map that showed how solar radiation processed the outflowing material and transformed it into the tenuous but spectacular display visible from Earth. The polarization properties of light scattered by dust in the tail provided yet another diagnostic of the physical processes occurring around the comet. The degree and orientation of polarization depended on the size, shape, and composition of dust particles, as well as the geometry of scattering relative to the Sun and Earth. By analyzing polarization measurements made at different wavelengths and viewing angles, astronomers could infer properties of individual dust grains that were far too small to be resolved directly by even the most powerful telescopes. These polarization studies revealed that the dust population around 3I/ATLAS was remarkably diverse, including both the fluffy, low-density aggregates typical of solar system comets and more compact crystalline particles that might represent a different formation environment or processing history. The discovery of crystalline silicate minerals in the dust was particularly intriguing, as these materials typically form at high temperatures that would not be expected in the cold outer regions of planetary systems where comets usually originate. The presence of these high-temperature minerals suggested that 3I/ATLAS might have formed in the inner regions of its parent system and been subsequently transported outward by gravitational interactions with giant planets. Alternatively, the crystalline materials might have been created by shock heating during the violent processes that ejected the comet from its birth system and sent it on its journey through interstellar space. Either scenario implied a formation history far more complex and dynamic than the simple accretion in cold outer regions assumed by traditional comet formation models. The chemical analysis of gas in the coma revealed isotopic ratios that provided direct evidence of the stellar nucleosynthesis processes that had created the heavy elements incorporated into the comet during its formation. The relative abundances of different isotopes of carbon, nitrogen, and oxygen carried signatures of the nuclear reactions that had occurred in the interior of the comet's parent star and in previous generations of stars that had contributed material to the interstellar medium from which the planetary system formed. These isotopic measurements represented a form of stellar archaeology that allowed astronomers to reconstruct the chemical evolution of the galaxy over billions of years. By comparing the isotopic signatures found in three I/ATLAS with those observed in other astronomical environments, scientists could trace the pathways through which elements created in stellar interiors were dispersed through space and incorporated into new generations of stars and planets. The discovery that interstellar objects carry such detailed records of galactic chemical evolution transformed their scientific value from curiosities to essential probes of cosmic history. Each visitor from another star system potentially carried unique information about the conditions and processes that existed at different times and locations in the galaxy's past. The realization that such objects might be relatively common, with perhaps dozens passing through the inner solar system each year, suggested that a systematic survey program could eventually assemble a comprehensive library of galactic chemical evolution. As 3 I/ATLAS continued its approach toward perihelion, the international coordination required to maximize the scientific return from observations reached unprecedented levels of complexity. Telescope time allocation committees worked around the clock to optimize observing schedules that would provide continuous coverage of the rapidly changing comet. Space agencies coordinated the pointing of multiple satellites to provide simultaneous observations at different wavelengths, while ground-based observers organized campaigns that would maintain surveillance of the comet as it moved across the sky. The data management challenges posed by this observational campaign pushed astronomical computing infrastructure to its limits. The volume of information being collected exceeded the capacity of traditional analysis pipelines, requiring the development of new algorithms and computational approaches that could extract meaningful scientific results from the flood of measurements. Machine learning techniques originally developed for other applications were adapted to identify subtle patterns and correlations in the multidimensional datasets being assembled by the global observing network. The collaborative spirit generated by the 3 I/ATLAS campaign also highlighted the international nature of modern astronomy and the ways in which scientific cooperation could transcend political and cultural boundaries. Astronomers from dozens of countries contributed observations, analysis techniques, and theoretical insights that collectively created a scientific understanding far richer than any single nation or institution could have achieved independently. As the comet's perihelion approached, public interest in the mission reached levels typically reserved for major space exploration milestones. The combination of the object's interstellar origins, its unprecedented collision with a solar storm, and the spectacular displays it was creating as it warmed under solar heating captured imaginations around the world. Educational institutions organized viewing events that introduced millions of people to the wonders of astronomical observation, while social media platforms buzzed with images and updates about the comet's behavior. The philosophical implications of studying a visitor from another star system resonated beyond the scientific community to broader discussions about humanity's place in the cosmos. Here was tangible evidence that the galaxy was a connected system where material, and perhaps even life itself, could travel between star systems over cosmic timescales. The possibility that objects from our own solar system might similarly be wandering through space, carrying Earth's chemical signature to distant worlds, added a poetic dimension to the scientific discoveries being made. The approach to perihelion also marked a transition in the comet's behavior from the relatively predictable warming and outgassing of its outer layers to the potentially more dramatic responses that might occur when solar heating penetrated to its deepest interior regions. Theoretical models suggested that reservoirs of highly volatile materials might exist in the comet's core, protected by insulating layers of less volatile ices and rocky debris. If these deep reservoirs were suddenly exposed to solar heating, they might create outbursts of activity far more intense than anything yet observed. The anticipation of these potential dramatic events added urgency to the observational campaign and influenced the strategic deployment of observational resources. Instruments capable of rapid response to sudden changes were positioned for continuous monitoring, while others were configured to capture detailed measurements of any explosive events that might occur. The scientific community prepared for the possibility that 3I/ATLAS might provide insights into cometary physics that would revolutionize understanding of these ancient remnants of planetary formation. As the final weeks before perihelion ticked away, the comet continued to evolve and surprise its observers with new manifestations of its alien nature. Each day brought fresh discoveries that added new chapters to the story of this wanderer from the stars, while simultaneously raising new questions about the processes that govern the behavior of objects formed in the diverse environments that exist throughout the galaxy. The mounting anticipation within the scientific community reached almost unbearable levels as 3I/ATLAS entered the final phase of its approach toward perihelion. October's crisp nights brought with them a sense of cosmic theatre, as if the universe itself was holding its breath before the climactic moment when this ancient wanderer would face its closest encounter with our sun. The comet had become more than just an astronomical object. It had transformed into a messenger carrying secrets from depths of space and time that human minds could barely fathom. The thermal evolution models, refined through countless iterations and fed with streams of real-time data from observatories around the globe, painted an increasingly dramatic picture of what might unfold in the coming days. As 3I/ATLAS spiraled ever closer to the sun, crossing invisible boundaries where temperatures rose exponentially with each passing hour, the models predicted that entirely new regions of the nucleus would begin to activate. These were not the surface layers that had been gently outgassing for months, but deeper reservoirs of exotic ices that had remained frozen solid throughout the comet's billion-year journey through the void. The chemistry hidden within these deeper layers promised revelations that could rewrite textbooks on planetary formation. Spectroscopic analysis of the gases already streaming from the comet had revealed trace amounts of molecules that hinted at the presence of compounds formed under conditions of extreme cold and pressure, perhaps in the shadows of giant planets or in the turbulent regions where stellar winds sculpted the outer reaches of planetary disks. If the heating now penetrating toward the nucleus's core succeeded in liberating these materials, astronomers would witness the release of a chemical library that had been sealed away since the epoch when planets were still condensing from cosmic dust. The gravitational dance between 3I/ATLAS and our Sun had begun to reveal subtle but measurable effects that spoke to the comet's internal architecture. As solar heating created temperature gradients within the nucleus, different regions expanded and contracted at different rates, generating internal stresses that occasionally manifested as sudden shifts in the comet's rotation period. These changes, measured with the precision that only modern astronomy could achieve, provided insights into the mechanical properties of materials that had been forged under alien skies billions of years ago. The magnetic environment surrounding the comet had evolved into something resembling a miniature version of the complex field structures found around active galaxies and stellar remnants. The interaction between outflowing gas from the nucleus and the solar wind had created a bow shock that accelerated particles to relativistic speeds, generating synchrotron radiation detectable across the electromagnetic spectrum from radio waves to X-rays. This natural particle accelerator provided a unique laboratory for studying fundamental physics processes under conditions that could never be replicated on Earth. Radio astronomers monitoring these emissions discovered that the comet's magnetic field structure exhibited periodicities that correlated with its rotation, suggesting that different regions of the nucleus possessed distinct magnetic properties. Some areas appeared to be weakly magnetized, consistent with the typical behavior of icy materials, while others showed surprisingly strong magnetic signatures that hinted at the presence of metallic inclusions, or perhaps even remnant magnetic fields frozen into the nucleus during its formation in the presence of a stellar magnetic environment. The wake that 3I/ATLAS carved through the solar wind had grown to encompass a volume of space larger than Earth's orbit, creating disturbances that propagated both upstream and downstream from the comet's position like ripples on a cosmic pond. Solar wind monitoring spacecraft positioned throughout the inner solar system detected these perturbations as subtle but persistent changes in the density and velocity of particles streaming from the Sun. The pattern of these disturbances provided yet another window into the comet's physical properties, revealing aspects of its mass distribution and volatile inventory that complemented the direct optical observations of its nucleus and coma. The dust environment around 3I/ATLAS had become a complex ecosystem of particles ranging in size from individual molecules to boulder-sized chunks of nucleus material. High-resolution imaging revealed that this dust was not distributed uniformly around the comet, but was organized into intricate patterns that reflected the geometry of gas jets and the influence of solar radiation pressure. Some regions showed dense concentrations of large particles that moved in highly eccentric orbits around the nucleus, while others were dominated by fine dust that formed gossamer streams extending millions of kilometers into space. The analysis of this dust population provided insights into the physical processes that had shaped the comet's nucleus over geological timescales. Some particles appeared to be pristine fragments that had been gently liberated from the surface by sublimating ice, preserving their original structure and composition. Others showed clear evidence of having been processed by shock waves and thermal cycling during explosive outgassing events, creating new mineral phases and textural modifications that told stories of violence and transformation in the seemingly peaceful environment around the comet. The isotopic composition of different dust components revealed a complex history of nuclear synthesis and chemical evolution that spanned multiple stellar generations. Some grains carried isotopic signatures characteristic of material processed in the interiors of massive stars that had ended their lives in spectacular supernova explosions, while others showed evidence of formation in the gentler environments around lower mass stars like our Sun. The coexistence of these diverse materials within a single object provided direct evidence of the mixing and homogenization processes that occur in interstellar space over cosmic timescales. The spectroscopic monitoring of gas in the coma had revealed the presence of molecular species that existed nowhere else in the solar system, complex organic compounds that formed through chemical reactions driven by solar ultraviolet radiation in the unique environment surrounding the nucleus. These molecules were unstable and short-lived, existing for only brief moments before being destroyed by further photochemical processing. But their detection provided insights into the chemical pathways through which simple compounds could evolve into more complex structures under the influence of stellar radiation. The discovery of these exotic molecules raised intriguing questions about the potential for chemical evolution in the environments around comets and asteroids throughout the galaxy. If such processes were common wherever stellar radiation interacted with volatile, rich materials, they might represent a previously unrecognized pathway for the formation of complex organic compounds in space. The implications extended beyond pure chemistry to questions about the origins of life itself, and the possibility that the building blocks of biology might be continuously created and destroyed in the dynamic environments around small bodies throughout the cosmos. The thermal infrared observations being conducted by space-based telescopes had begun to reveal temperature gradients across the surface of the nucleus that painted a detailed picture of how solar energy was absorbed, conducted, and re-radiated by different materials. Some regions appeared to be covered with dark, organic-rich mantles that absorbed sunlight efficiently but conducted heat poorly, creating steep temperature gradients that led to explosive sublimation when critical thresholds were exceeded. Other areas showed the thermal signatures of exposed ice, which absorbed less solar energy but conducted heat more efficiently, leading to gentler, more sustained outgassing. These thermal maps provided the foundation for increasingly sophisticated models of the comet's internal structure and the processes governing its response to solar heating. The models suggested that the nucleus was not a simple mixture of ice and rock, but rather a complex assemblage of distinct layers and domains, each with its own thermal history and volatile inventory. The boundaries between these regions created discontinuities that could focus thermal stresses and create the conditions for sudden violent eruptions when material from one domain was suddenly exposed to conditions appropriate for another. The gravitational field mapping being conducted through precise tracking of the comet's trajectory had revealed density variations within the nucleus that confirmed the presence of this complex internal structure. Some regions appeared to be relatively dense, consistent with concentrations of rocky or metallic materials, while others showed the low densities characteristic of fluffy, ice-rich assemblages. The pattern of these density variations suggested that 3I/ATLAS might be what planetary scientists term a contact binary, two separate objects that had gently collided and stuck together during the early stages of planetary system formation. If this interpretation was correct, it would explain many of the puzzling aspects of the comet's behavior, including the complex patterns of outgassing activity and the presence of distinct chemical domains within the nucleus. Each component of the binary might have formed under different conditions and retained its own unique composition and structure, creating a kind of natural laboratory for studying the diversity of materials and processes that existed in the outer regions of planetary systems during the epoch of world formation. The polarization studies being conducted on light scattered by dust in the coma and tail had revealed particle populations with optical properties, unlike anything found in solar system comets. Some dust grains showed polarization signatures characteristic of crystalline silicate minerals that typically form at high temperatures, while others exhibited the properties of amorphous materials that condense under conditions of rapid cooling. The coexistence of these different particle types within the same object suggested a formation history that involved both high-temperature processing and subsequent cooling in the cold environment of the outer planetary system. The discovery of high-temperature minerals in an object that presumably formed in the cold outer reaches of another star system raised fundamental questions about the processes that govern the distribution of materials during planetary formation. One possibility was that 3I/ATLAS had originally formed closer to its parent star and been subsequently transported outward by gravitational interactions with giant planets. Alternatively, the high-temperature minerals might have been created during the violent processes that ejected the comet from its birth system, perhaps through shock heating during close encounters with other objects or through exposure to intense stellar winds during periods of enhanced stellar activity. The chemical analysis of different molecular species in the coma had revealed abundance patterns that provided clues about the oxidation state and pressure conditions that existed during the comet's formation. Some compounds were consistent with formation in a highly reducing environment similar to the outer solar nebula that gave birth to our own planetary system, while others suggested exposure to more oxidizing conditions that might exist in the vicinity of different types of stars or in regions where stellar winds create unique chemical environments. These chemical signatures served as a kind of forensic evidence that allowed astronomers to reconstruct aspects of the environment that existed in the comet's birth system billions of years ago. The relative abundances of different isotopes provided information about the stellar nucleosynthesis processes that had created the heavy elements incorporated into the comet, while the molecular ratios revealed details about the temperature, pressure, and chemical gradients that existed in the comet protoplanetary disk from which it condensed. The coordination of observations during the final approach to perihelion had created an unprecedented real-time collaboration that spanned continents and involved hundreds of researchers working around the clock to capture every aspect of the comet's behavior. As 3I/ATLAS moved across the sky, different observatories took up the watch in a carefully choreographed sequence that ensured continuous coverage despite the rotation of Earth and the changing positions of space-based instruments. The data streams flowing from this global network of observers had grown so voluminous that new computational approaches had to be developed just to process and analyze the information in real time. Machine learning algorithms trained on simulated comet behavior worked alongside traditional analysis techniques to identify patterns and anomalies in the observations that might otherwise have been lost in the flood of data. The result was a level of scientific understanding that evolved hour by hour as new measurements refined and sometimes revolutionized theoretical models of cometary behavior. The public engagement generated by the 3I/ATLAS mission had created a global community of citizen scientists who contributed their own observations and analysis to the professional research effort. Amateur astronomers with modest equipment found that they could make meaningful contributions to the study of specific aspects of the comet's behavior, while educational institutions organized observing programs that introduced students to the excitement of real scientific discovery. The philosophical implications of studying this messenger from another star had begun to permeate discussions far beyond the astronomical community. The realization that objects could carry chemical and physical information between star systems over cosmic timescales suggested that the galaxy was a much more connected and dynamic place than previously imagined. The possibility that life itself might spread between worlds through natural processes of planetary system evolution added profound new dimensions to questions about the prevalence and distribution of biology throughout the cosmos. As the hours until perihelion dwindled to mere days, the intensity of activity around 3I/ATLAS reached levels that strained the capabilities of even the most sophisticated observational instruments. The comet had become one of the brightest objects in the inner solar system, visible to the naked eye from dark locations on Earth as a fuzzy star with a faint tail that stretched across several degrees of sky. The transformation from a faint speck of light, detectable only by the most sensitive telescopes, to a spectacular naked-eye object had occurred over just a few months, compressed into a time frame that allowed human observers to witness the complete evolution of an interstellar visitor's response to solar heating. The spectroscopic signatures of gases streaming from the nucleus had grown so complex that new analysis techniques had to be developed to disentangle the overlapping contributions of dozens of different molecular species. Each compound told part of the story of the comet's internal composition and the physical processes governing its response to solar radiation. But the complete picture required the integration of information across the entire electromagnetic spectrum, from radio waves to gamma rays. The magnetic field measurements being conducted by solar wind monitoring spacecraft had revealed that the comet's interaction with the interplanetary medium had created a complex structure of shocks, current sheets, and field line draping that extended far beyond the visible coma. This magnetic environment was constantly evolving as changes in solar wind conditions and variations in the comet's outgassing rate created new configurations of field lines and particle acceleration regions. The radio emissions generated by these magnetic processes had become strong enough to be detected by amateur radio astronomers using relatively simple equipment, creating opportunities for public participation in the study of fundamental plasma physics processes occurring around the comet. The signals carried information about particle acceleration, magnetic reconnection, and wave-particle interactions that provided insights into similar processes occurring throughout the galaxy, wherever magnetic fields and charged particles interact under extreme conditions. The dust analysis being conducted by infrared telescopes had revealed particle populations with thermal properties that suggested formation under conditions quite different from those that created the dust in solar system comets. Some grains appeared to have condensed directly from hot stellar winds, while others showed evidence of processing in the cold, tenuous environment of interstellar space over timescales measured in hundreds of millions of years. The size distribution of dust particles had evolved as the comet approached the Sun, with smaller grains being preferentially removed by radiation pressure, while larger chunks remained in the vicinity of the nucleus. This natural sorting process created gradients in particle properties throughout the coma and tail that provided additional information about the physical processes governing dust production and transport in cometary environments. The polarization properties of light scattered by this dust had revealed optical characteristics that challenged theoretical models of how particles interact with electromagnetic radiation under the unique conditions that exist around comets. The observations suggested that traditional approaches to modeling light scattering might be inadequate for describing the behavior of particles that had been processed by cosmic ray bombardment during long residence in interstellar space. As 3 I/ATLAS entered the final phase of its approach to perihelion, the scientific community prepared for the possibility that the most dramatic revelations were still to come. Deep within the comet's nucleus, reservoirs of highly volatile materials might still be waiting to be liberated by the penetrating warmth of solar radiation. If these materials were suddenly exposed to the vacuum of space, they might create outbursts of activity that would dwarf everything observed so far and provide unprecedented insights into the most exotic chemistry that could exist in the frozen heart of an interstellar wanderer. The anticipation was palpable in observatories around the world as astronomers adjusted their instruments and prepared to capture whatever spectacular finale this visitor from the stars might provide. The stage was set for a cosmic performance that would unfold over the course of just a few days, but might provide scientific insights that would influence our understanding of planetary formation and galactic evolution for generations to come. The approaching perihelion represented more than just the climax of 3 I/ATLAS's journey through our solar system. It marked a moment when the boundaries between stellar systems dissolved and the universe revealed itself as a single, interconnected tapestry where matter and energy, chemistry and physics, past and future, all converged in the gentle warming of ancient ice under alien starlight. The day of perihelion dawned with observatories across 7 continents, humming with anticipation, their instruments trained on a patch of sky where 3 I/ATLAS was about to write the final chapter of its solar encounter. At precisely 13 hours and 47 minutes, universal time on October 30th, this ancient wanderer would reach its closest approach to our sun, a moment that had been billions of years in the making. The mathematics were elegant in their precision. 1.4 astronomical units, roughly 210 million kilometers, the minimum distance that this visitor from the stars would achieve before beginning its long journey back toward the cosmic dark. But mathematics could not capture the poetry of what was unfolding in the depths of space. As 3 I/ATLAS crossed this invisible threshold, solar radiation was penetrating deeper into its nucleus than ever before, reaching reservoirs of material that had remained undisturbed since the comet's formation in the outer reaches of an alien world. The thermal wave spreading inward from the surface moved at the pace of geological processes, measured in hours rather than the millennia typically associated with changes in such ancient objects. Yet each passing moment brought the potential for revelations that could reshape our understanding of how worlds form and evolve throughout the galaxy. The first signs that something extraordinary was beginning came not from optical telescopes, but from radio observatories monitoring the electromagnetic environment around the comet. Deep Space Network antennas detected sudden bursts of radio emission that suggested violent reorganization of magnetic fields in the space surrounding the nucleus. These signals arrived at Earth carrying information about processes occurring in real time around 3I/ATLAS, electromagnetic signatures of particle acceleration and field line reconnection that painted a picture of increasing chaos in the comet's immediate environment. The optical observers were not far behind in detecting the beginning of what would become known as the Great Outburst. High-resolution cameras aboard space telescopes captured the first images of jets erupting from previously quiet regions of the nucleus, fountains of gas and dust that appeared suddenly and grew in brightness and extent over the course of minutes, rather than the hours or days that typically characterized changes in cometary activity. These were not the gentle, steady emissions that had marked the comet's behavior during its months-long approach, but violent explosions that spoke of sudden pressure release, as deeply buried volatile materials were finally liberated by penetrating solar heat. The spectroscopic analysis of these new jets revealed chemical signatures unlike anything previously detected in the comet's emissions. Complex organic molecules that required specific temperature and pressure conditions to form began appearing in the spectra, compounds that could only have originated from regions deep within the nucleus, where different chemical environments had been preserved, like fossils from the comet's formation epoch. The presence of these materials provided direct evidence that 3I/ATLAS possessed internal structure far more sophisticated than anyone had imagined, with distinct chemical domains that reflected the varied conditions under which different parts of the nucleus had originally condensed from the protoplanetary disk around its parent star. The dust production rate increased by orders of magnitude as these deep reservoirs were tapped, creating an expanding cloud of debris that transformed the comet's appearance from a relatively compact object with a modest tail into a spectacular display that dominated the inner solar system's dust environment. The particles streaming away from the nucleus carried with them isotopic signatures that told stories of stellar nucleosynthesis and galactic chemical evolution spanning multiple generations of stars, each grain a tiny time capsule preserving information about conditions that existed billions of years ago in a stellar system light years away. The gravitational perturbations caused by these massive outbursts began to have measurable effects on the comet's trajectory and rotation state that went far beyond the subtle changes that had been detected during the earlier phases of its approach. The asymmetric thrust created by jets erupting from different regions of the nucleus generated torques that altered the comet's spin period and orientation in ways that could be detected by precise astrometric measurements. These changes provided real-time information about the mass and momentum of material being ejected, allowing astronomers to estimate the energy of the processes occurring deep within the nucleus. The magnetic field measurements being conducted by solar wind monitoring spacecraft revealed that the eruptions were creating shock waves that propagated outward through the interplanetary medium, like ripples on a pond. These disturbances carried information about the violence of the processes occurring at the comet's surface and created temporary modifications in the solar wind flow that could be detected millions of kilometers away from the source. The comet had become a powerful source of space weather, generating its own storms in the sea of charged particles flowing from the sun. The thermal infrared observations showed temperature spikes across the nucleus surface that indicated the exposure of fresh ice and rock as overlying layers were stripped away by the explosive outgassing. Some regions reached temperatures far above the sublimation point of water ice, suggesting that the heating was being driven not just by absorbed solar radiation, but by the energy release associated with the rapid expansion of pressurized gases escaping from the interior. The nucleus was literally tearing itself apart as billions of years of accumulated volatile materials sought equilibrium with the vacuum of space. The polarization measurements of light scattered by the expanding dust cloud revealed particle populations with optical properties that provided insights into the physical processes governing the disruption of the nucleus material. Some grains appeared to be pristine fragments of the original cometary material, liberated gently by sublimating ice, while others showed clear evidence of having been processed by shock waves and thermal cycling during the violent eruption process. The relative proportions of these different particle types provided information about the mechanisms through which solid materials were being converted into the expanding debris cloud. The radio astronomy teams detected emissions from the magnetic environment around the comet that suggested the formation of particle acceleration regions where electrons and ions were being boosted to relativistic energies. These natural particle accelerators were creating synchrotron radiation across a broad range of frequencies, from the radio waves detectable by ground-based telescopes to the high-energy emissions observable only by space-based instruments designed to study cosmic ray interactions and stellar wind physics. The wake structure that 3I/ATLAS was carving through the solar wind had evolved into something resembling the complex flow patterns found around much larger objects like planets and moons. The comet's enhanced outgassing had created a substantial obstacle to the solar wind flow, generating bow shocks and magneto-tail structures that extended far beyond the visible coma. Solar wind monitoring spacecraft positioned throughout the inner solar system detected the passage of these disturbances as changes in the magnetic field orientation and particle density that persisted for hours after the initial shock passage. The dust environment around the comet had become so dense that it began to affect the propagation of electromagnetic radiation through the region, creating scattering and absorption effects that influenced observations across multiple wavelengths. This natural laboratory provided opportunities to study light-matter interactions under conditions of particle density and composition that could not be replicated in terrestrial experiments, offering insights into fundamental physics processes that occur in dusty environments throughout the galaxy. The chemical analysis of the gases streaming from the newly active regions and temperature conditions that existed in the core revealed molecular species that provided direct evidence of the pressuremet's deep interior. Some compounds could only form under specific combinations of temperature and pressure, creating natural thermometers and barometers that allowed scientists to reconstruct the physical conditions that existed within the nucleus before the disruption began. The results painted a picture of internal pressures far higher than theoretical models had predicted, suggesting that volatile materials had been trapped under significant overburden of less volatile ices and rocky debris. The isotopic analysis of different molecular species revealed chemical gradients within the nucleus that reflected the thermal and chemical evolution of the comet during its formation and subsequent history. Materials from different depths showed distinct isotopic signatures that could be correlated with different epochs in the chemical evolution of the protoplanetary disk from which the comet had condensed. The deepest materials carried isotopic fingerprints of the earliest stages of planetary system formation, when stellar winds and radiation fields were still sculpting the chemistry of the outer disk regions. The coordination of observations during this climactic phase required unprecedented levels of international cooperation and real-time communication between observatories around the world. As the comet's activity evolved on timescales of minutes and hours, telescope operators had to continuously adjust their observing strategies to capture the most scientifically valuable data while the phenomena were actually occurring. The result was a data set of extraordinary richness and temporal resolution that provided insights into cometary physics processes that had never before been observed in such detail. The public engagement generated by the spectacular display reached levels that rivaled major space exploration milestones, with live streams from major observatories drawing millions of viewers who watched in real time as this visitor from another star system revealed its ancient secrets. Educational institutions organized special viewing events that allowed students and the general public to participate in the excitement of scientific discovery as it unfolded, creating connections between the research community and society at large that highlighted the universal appeal of exploring the cosmos. The philosophical implications of witnessing such intimate details of an interstellar object's behavior resonated far beyond the scientific community, touching on fundamental questions about the nature of matter, energy, and information transfer between stellar systems. Here was direct evidence that the galaxy was a dynamic, interconnected system where materials and perhaps even the building blocks of life itself could travel between worlds, over cosmic timescales, carried by natural processes that operated on scales both vast and intimate. The data streaming from the global network of observatories began to reveal that the Great Outburst was not a single event, but rather a complex sequence of eruptions that reflected the internal structure and composition of the nucleus in ways that would require years of analysis to fully understand. Each new jet that appeared carried its own chemical signature and particle population, creating a kind of natural core sample that revealed the three-dimensional architecture of materials within the comet that had been assembled billions of years ago in the outer reaches of an alien planetary system. The magnetic field measurements showed that the eruptions were creating a complex and rapidly evolving electromagnetic environment that influenced the propagation of charged particles throughout the region around the comet. The interaction between outflowing gas and the solar wind generated current systems and field line configurations that created natural waveguides for electromagnetic radiation, focusing and amplifying signals in ways that enhanced the comet's radio emissions and made it briefly one of the strongest non-thermal radio sources in the inner solar system. The gravitational field mapping revealed that the mass loss associated with the outbursts was beginning to have measurable effects on the comet's overall structure and stability. The ejection of billions of tons of material was creating an imbalance that affected the nucleus's rotation and potentially its long-term structural integrity. Some theoretical models suggested that if the mass loss continued at the observed rate, significant portions of the nucleus might be completely disrupted, creating a debris field that would persist long after the comet had departed the inner solar system. The thermal evolution models, continuously updated with real-time temperature measurements from infrared telescopes, painted an increasingly dramatic picture of the processes occurring within the nucleus. The penetration of the thermal wave into the comet's interior was accelerating as insulating layers were stripped away by outgassing, exposing deeper materials to direct solar heating at rates that created positive feedback loops. Each eruption removed material that had been protecting underlying layers, allowing solar radiation to penetrate even further and trigger additional episodes of violent activity. The dust analysis revealed particle populations with mineral compositions that provided insights into the pressure and temperature conditions that existed during the original formation of the nucleus materials. Some grains showed evidence of having formed under conditions of high pressure that could only exist in the presence of significant gravitational compression, while others displayed the characteristics of rapid condensation in low-pressure environments. The coexistence of these different formation signatures within a single object provided direct evidence of the complex and dynamic processes that governed solid material assembly during the early stages of planetary system evolution. The spectroscopic monitoring of the expanding gas cloud revealed chemical reaction networks of extraordinary complexity as different molecular species interacted under the influence of solar ultraviolet radiation and the unique density and temperature conditions that existed in the comet's immediate environment. These reactions were creating new compounds that had never been observed in any astronomical environment, providing insights into the chemical pathways through which simple molecules could evolve into more complex structures under the influence of stellar radiation and magnetic fields. The polarization studies of light scattered by the dust in the expanding debris cloud revealed particle alignments and orientations that reflected the influence of magnetic fields and radiation pressure in organizing the material flow away from the nucleus. The patterns observed provided information about the electromagnetic environment around the comet and the ways in which charged dust grains responded to the complex field configurations created by the interaction between outflowing gas and the solar wind. The radio emissions from the comet's magnetic environment had grown strong enough to be detected by amateur radio operators around the world, creating opportunities for citizen scientists to contribute to the professional research effort by monitoring the time variability and spectral characteristics of the signals. The distributed network of amateur radio telescopes provided coverage and temporal resolution that complemented the observations being made by major professional facilities, demonstrating the value of public participation in cutting-edge astronomical research. The wake structure that the comet was creating in the solar wind had become so pronounced that it was beginning to influence space weather conditions throughout the inner solar system. Satellites monitoring the interplanetary medium detected the passage of shockwaves and magnetic field disturbances that originated from the comet's interaction with the solar wind, creating temporary modifications in the radiation environment that could affect spacecraft operations and even influence the behavior of Earth's magnetosphere. The coordination challenges posed by the rapidly evolving situation required the development of new protocols for real-time communication and data sharing between observatories that had never before been tested under such demanding conditions. The success of these coordination efforts created a template for future collaborative observations of transient astronomical phenomena and demonstrated the power of international scientific cooperation in addressing complex research challenges. As the hours passed and 3I/ATLAS continued its close encounter with our Sun, the comet's behavior entered an even more dramatic phase that challenged the capabilities of observational instruments and the theoretical frameworks used to understand cometary physics. The Great Outburst had evolved into what could only be described as a controlled disintegration, a carefully orchestrated dance between gravity, thermal energy, and chemical forces that was simultaneously destroying and revealing the ancient structure of this messenger from the stars. The nucleus, once a relatively compact object with well-defined boundaries, had become something more akin to a loosely bound swarm of fragments and debris held together by gravity and the complex flow patterns of outgassing material. High-resolution imaging revealed individual chunks of nucleus material tumbling through space in eccentric orbits around the central concentration of mass, each following its own trajectory determined by the balance between gravitational attraction and the momentum imparted by gas jets and radiation pressure. These fragments, ranging in size from house-sized boulders to microscopic grains, each told their own part of the story of 3I/ATLAS's formation and evolution. Spectroscopic analysis of individual pieces revealed chemical compositions that varied dramatically from fragment to fragment, suggesting that the original nucleus had been assembled from materials that formed under quite different conditions within the protoplanetary disk of its birth system. Some fragments showed the signatures of high-temperature processing, while others preserved the chemical fingerprints of condensation in the cold outer regions where giant planets sculpt the architecture of debris populations. The gravitational mapping of this evolving debris field revealed mass concentrations and void regions that reflected the internal structure that had existed within the original nucleus before its disruption began. Dense, rocky cores that had once been buried deep within the comet were now exposed to direct observation, while regions that had been rich in volatile ices had been completely excavated by outgassing, leaving behind hollow spaces that gradually filled with expanding gas and dust. The magnetic field measurements showed that each major fragment retained its own electromagnetic signature, creating a complex network of interacting field regions that generated radio emissions through mechanisms that were only beginning to be understood. The overall magnetic environment around the disrupting comet resembled a miniature version of the complex field structures found in stellar wind interaction regions, but operating on spatial and temporal scales that allowed detailed study of processes that were typically observable only as distant, unresolved phenomena in other astronomical contexts. The thermal infrared observations revealed temperature distributions across the debris field that painted a detailed picture of how solar energy was being absorbed and re-radiated by materials of different compositions and thermal properties. The newly exposed surfaces of fragments that had been buried within the nucleus showed temperatures far different from those predicted by simple thermal models, reflecting the complex interplay between absorbed solar radiation, conducted heat from neighboring fragments, and the cooling effect of sublimating volatile materials. The chemical evolution of the gas expanding away from the debris field showed evidence of reactions and processes that had never been observed in any cometary environment. The high density of reactive species created by the simultaneous outgassing of multiple fragment types had generated a natural chemical reactor where molecules were being synthesized and destroyed at rates that challenged theoretical models of gas phase chemistry under low-density conditions. The dust production from the disrupting nucleus had reached levels that began to influence the optical properties of the entire inner solar system environment. The expanding cloud of debris created by 3I/ATLAS was scattering and absorbing sunlight in ways that could be detected by sensitive photometric measurements of other solar system objects, effectively turning the comet into a natural laboratory for studying light-matter interactions on scales impossible to achieve through terrestrial experiments. The isotopic analysis of different fragment types revealed chemical signatures that provided direct evidence of the stellar nuclear synthesis processes that had created the heavy elements incorporated into the comet during its formation. The diversity of isotopic ratios found in different materials suggested that the comet's parent system had been enriched by multiple generations of stellar evolution, with contributions from both low-mass stars that had ended their lives as white dwarfs and massive stars that had exploded as supernovae. The polarization measurements of light scattered by the expanding debris cloud revealed particle alignment effects that reflected the influence of magnetic fields and radiation pressure in organizing the material flow away from the disrupting nucleus. The patterns observed provided unprecedented insights into the electromagnetic environment around the comet and the ways in which charged particles responded to the complex field configurations created by the interaction between multiple outgassing sources and the solar wind. The radio astronomy observations had detected emissions from particle acceleration regions distributed throughout the debris field, suggesting that the disruption process was creating multiple sites where electrons and ions were being boosted to high energies through magnetic reconnection and shockwave acceleration. These natural particle accelerators were generating electromagnetic radiation across a broad range of frequencies that provided insights into fundamental plasma physics processes occurring under conditions that could never be replicated in laboratory experiments. The wake structure that the disrupting comet was creating in the solar wind had evolved into something resembling the complex flow patterns found around planetary magnetospheres, but with the added complexity of multiple source regions and time-variable boundary conditions. Solar wind monitoring spacecraft detected shock waves, magnetic field rotations, and particle acceleration signatures that reflected the chaotic nature of the interaction between the expanding debris field and the interplanetary medium. The coordination of observations during this unprecedented event required continuous adaptation of observing strategies as the comet's behavior evolved on timescales that challenged traditional approaches to astronomical campaign planning. The success of this effort demonstrated the potential for real-time, adaptive observation strategies that could be applied to future studies of transient phenomena throughout the solar system and beyond. The public engagement generated by the spectacular disruption of 3I/ATLAS reached levels that transformed the event into a cultural phenomenon that extended far beyond the scientific community. The real-time nature of the observations allowed millions of people around the world to follow the comet's evolution as it happened, creating a shared experience of scientific discovery that highlighted the universal appeal of exploring the cosmos and understanding our place within the vast community of worlds that populate the galaxy. The philosophical implications of witnessing the detailed disruption of an interstellar object resonated deeply with questions about the transient nature of cosmic structures and the processes through which matter and energy are redistributed throughout the galaxy over cosmic timescales. The comet's transformation from a single, coherent object into a distributed collection of fragments and debris provided a vivid demonstration of the dynamic processes that continuously reshape the contents of planetary systems and distribute materials between stellar environments. The data being collected during this climactic phase of 3I/ATLAS's solar encounter would provide the foundation for theoretical developments in cometary physics, interstellar object studies, and planetary formation processes that would influence astronomical research for decades to come. Each measurement added another piece to the complex puzzle of understanding how worlds form and evolve throughout the galaxy, and how the chemical and physical processes that govern these transformations create the conditions necessary for the emergence of complexity and perhaps even life itself. As the disruption continued and the fragments of 3I/ATLAS began their long journey back toward the cosmic dark, astronomers realized they had witnessed something far more significant than the mere warming and outgassing of an ancient comet. They had observed the detailed deconstruction of a world that carried within its structure the history of planetary formation processes that occurred billions of years ago around a star whose light had not yet reached Earth when life first emerged in our own oceans. The chemical signatures, isotopic ratios, and physical structures revealed during the comet's solar encounter would provide insights into the diversity of conditions and processes that exist throughout the galaxy, expanding our understanding of the cosmic context within which our own world had formed and evolved. The legacy of 3I/ATLAS extended far beyond the immediate scientific discoveries it had enabled, touching on fundamental questions about the interconnected nature of the galaxy and the ways in which matter, energy, and perhaps even information could travel between stellar systems over the vast timescales of cosmic evolution. As the fragments of this ancient wanderer began their journey back toward interstellar space, they carried with them not only the chemical signatures of their alien origins, but also the subtle modifications imparted by their encounter with our Sun, creating a kind of cosmic exchange that linked our solar system with the distant stellar environment from which the comet had originated billions of years ago. The gentle warming of ancient ice under the light of an alien star had revealed secrets that transformed our understanding of the galaxy as a living, breathing system, where worlds and stars existed not in isolation, but as part of a vast, interconnected web of matter and energy that stretched across space and time on scales that humbled human imagination, while simultaneously filling the heart with wonder at the magnificent complexity of creation that unfolds in the darkness between the stars. The spectacle that unfolded as 3I/ATLAS rounded the Sun marked not just the climax of its solar encounter, but the beginning of humanity's deeper understanding of what it truly means to be citizens of a galaxy. As the disrupted fragments began their slow dance away from perihelion, each piece carrying its own trajectory and chemical signature, astronomers found themselves witnesses to something that challenged the very foundations of how we think about planetary systems and their boundaries. The outbound journey revealed phenomena that had been impossible to predict during the comet's approach. As solar heating began to wane and the most volatile materials finished their violent escape into space, the remaining fragments underwent a kind of cosmic metamorphosis. The thermal cycling between day and night sides of tumbling chunks created stress patterns that caused some pieces to split further, while others seemed to develop protective crusts of non-volatile residue that would shield their interiors during the long journey back to interstellar space. The chemistry of this transformation fascinated researchers who realized they were observing the birth of a new class of interstellar objects. These fragments, now modified by their passage through our solar system, would carry with them isotopic signatures and mineral phases that had been created through interaction with our Sun's radiation and magnetic field. In essence, 3I/ATLAS was becoming a messenger that would eventually carry news of our solar system to whatever distant realm it might encounter in the cosmic future. The gravitational dynamics of the fragment field created natural experiments in celestial mechanics that provided insights into how asteroid families and comet populations evolve over geological timescales. Some pieces moved in nearly identical trajectories that would keep them gravitationally associated for millions of years, while others followed divergent paths that would eventually separate them by light years. The range of outcomes demonstrated the sensitivity of orbital dynamics to small perturbations and showed how single disruption events could seed multiple star systems with related materials over cosmic time. The magnetic field evolution around the departing fragments revealed unexpected persistence in the electromagnetic signatures that had been generated during the intense activity near perihelion. Even as outgassing rates declined and the density of charged particles decreased, organized field structures continued to channel and accelerate the remaining ions and electrons. These residual acceleration regions created fading but detectable radio emissions that could be tracked long after the visible activity had subsided. The dust trails left by different fragments began to diverge and spread under the influence of radiation pressure and gravitational perturbations from the planets. Each trail carried its own population of particles with distinct size distributions and compositions that reflected the specific conditions under which that fragment had been disrupted. The resulting debris streams would eventually spread throughout the solar system, with some particles destined to impact planetary atmospheres where their exotic chemistry could be studied through meteor spectroscopy for decades to come. The isotopic analysis of the most recently liberated materials revealed chemical signatures that had been protected in the deepest interior regions of the original nucleus. These pristine samples carried information about the earliest stages of solid condensation in the comet's birth system, preserving records of temperature and pressure gradients that had existed in the protoplanetary disk before planetary formation had begun to homogenize conditions through gravitational stirring and collisional processing. The thermal evolution of the fragments as they moved away from the Sun provided a natural laboratory for studying how materials with exotic compositions responded to the gradual cooling that would characterize their return journey to interstellar space. Some fragments showed evidence of phase transitions as different mineral species underwent structural changes at specific temperature thresholds, while others exhibited more gradual evolution that reflected the complex interplay between internal heat conduction and radiative cooling to space. The wake structures created by the fragment field in the solar wind evolved into a complex pattern of intersecting shock waves and magnetic field disturbances that provided insights into fluid dynamics processes operating under conditions of variable source strength and geometry. The interaction between multiple outgassing sources created interference patterns in the surrounding plasma that could be studied using the distributed network of solar wind monitoring spacecraft positioned throughout the inner solar system. The spectroscopic monitoring of individual fragments revealed that each piece was developing its own unique chemical signature as different surface materials were preferentially removed by continued outgassing and solar wind sputtering. This natural fractionation process created a kind of chemical fingerprinting that would allow astronomers to identify fragments belonging to the 3I/A TLAS family, even after they had dispersed throughout the galaxy over millions of years. The polarization studies of light scattered by dust from different fragments showed that the disruption process had created particle populations with optical properties that varied systematically with the original location of material within the nucleus. Fragments from the outer layers produced dust with different scattering characteristics than those from the interior regions, providing insights into the three-dimensional structure that had existed within the original comet before its encounter with solar heating. The radio astronomy observations detected the gradual fading of electromagnetic emissions from the fragment field as particle densities decreased and magnetic field strengths weakened. The decay rates of different emission components provided information about the physical processes that had sustained the radio sources during the peak activity phase and offered insights into similar phenomena that might occur around other disrupting comets throughout the galaxy. The gravitational field mapping revealed that several of the largest fragments retained sufficient mass to maintain their own debris clouds of smaller particles and gas. These miniature coma structures evolved independently as each fragment followed its own thermal and dynamical history, creating multiple laboratories for studying cometary physics processes under slightly different boundary conditions. The chemical reaction networks in the expanding gas clouds around different fragments showed evidence of continued molecular synthesis, even as densities declined and temperatures dropped. The chemistry was sustained by the energy deposited in excited molecular states during the violent disruption phase, creating a kind of chemical memory that allowed complex reactions to continue long after the initial energy input had ended. The dust environment around the fragment field had become so extended that it began to influence zodiacal light observations and meteor detection rates throughout the solar system. The exotic composition of three I/ATLAS debris created spectroscopic signatures that could be distinguished from native solar system materials, providing a natural tracer for studying the dispersal and evolution of interstellar matter within planetary system environments. The magnetic reconnection events occurring at the boundaries between different fragment magnetospheres generated particle acceleration signatures that could be detected by cosmic ray monitoring stations on Earth and throughout the solar system. These natural accelerators were creating high-energy particles with energy spectra and composition signatures that provided insights into fundamental plasma physics processes operating under extreme conditions. The thermal infrared observations showed that different fragments were cooling at rates that reflected their internal structure and composition. Dense, rocky pieces retained heat longer than fluffy, ice-rich assemblages, creating temperature gradients within the fragment field that would persist for years as the debris dispersed throughout the outer solar system. The isotopic evolution of gas emissions from individual fragments revealed evidence of continued nuclear processing through cosmic ray interactions that modified the relative abundances of different isotopes at measurable rates. This natural nuclear reactor provided insights into the mechanisms through which stellar nucleosynthesis products were further processed during their journey through interstellar space. The coordination of observations during the outbound phase required adaptation of traditional follow-up strategies to account for the distributed nature of the target and the need to track multiple objects simultaneously across wide areas of sky. The success of this effort demonstrated new approaches to multi-object astronomical campaigns that would prove valuable for future studies of disrupted comets and asteroid family formation events. The public engagement during this phase of the mission evolved from the excitement of witnessing dramatic eruptions to the deeper satisfaction of understanding how cosmic processes operated over extended timescales. Educational institutions organized long-term monitoring programs that allowed students to participate in tracking the evolution of individual fragments and contributed to the professional research database through systematic observations extending over months and years. The philosophical implications of watching 3I/ATLAS transform from a single visitor into a distributed family of interstellar wanderers touched on questions about identity and continuity in cosmic processes. The fragments carried within them the history of their common origin, while simultaneously developing individual characteristics that reflected their unique responses to solar system conditions. This duality between unity and diversity provided a powerful metaphor for understanding how complexity emerged from simplicity throughout the universe. The theoretical developments stimulated by the 3I/ATLAS observations began to influence models of planetary system formation and evolution throughout the galaxy. The detailed measurements of disruption processes, chemical fractionation, and fragment dynamics provided constraints on theoretical frameworks that had previously relied on sparse observational data and simplified assumptions about cometary behavior under extreme conditions. The data archives created by the Global Observational Campaign represented an unprecedented resource for future research into interstellar object physics and the processes that govern material exchange between stellar systems. The temporal coverage and multi-wavelength scope of the observations created a comprehensive record that would support investigations into aspects of the comet's behavior that might not become apparent until years of analysis had been completed. The technological innovations developed to handle the real-time coordination and data processing challenges posed by 3I/ATLAS established new standards for responsive astronomical observations that could be applied to future transient phenomena throughout the solar system and beyond. The success of adaptive observing strategies and distributed data analysis techniques demonstrated the potential for more flexible and efficient approaches to large-scale collaborative research projects. The legacy of 3I/ATLAS extended beyond the immediate scientific discoveries to encompass broader questions about the role of chance encounters in cosmic evolution and the mechanisms through which information about distant environments could be preserved and transported across galactic distances. Each fragment now departing our solar system carried within its structure and composition a record not only of its alien origins, but also of its transformative encounter with our Sun, creating a kind of cosmic correspondence that linked our local stellar environment with distant regions of the galaxy in ways that previous generations of astronomers could hardly have imagined. The gentle dispersal of ancient ice and rock back toward the interstellar void marked not an ending, but a transformation, as 3I/ATLAS evolved from a single mysterious visitor into a family of messengers that would continue their journey through the galaxy, carrying with them the secrets of two stellar systems and the story of their brief but spectacular encounter in the space between worlds. The universe had revealed itself once again as a place where boundaries dissolved and connections formed across distances and timescales that challenged human comprehension, while simultaneously inspiring wonder at the magnificent choreography of matter and energy that played out in the endless dance of creation among the stars. As the final fragments of 3I/ATLAS began their slow fade into the cosmic background, astronomers found themselves not at the conclusion of an extraordinary encounter, but at the threshold of understanding that would reshape their conception of how matter travels between worlds. The comet's transformation had created a natural experiment on galactic scales, seeding multiple trajectories with chemically distinct materials that would eventually reach destinations scattered throughout the Milky Way, each carrying its own part of the story written during those remarkable months when an ancient wanderer met our Sun. The implications rippled outward like gentle waves through the scientific community, touching every field from planetary formation theory to astrobiology, as researchers began to grasp that they lived in a galaxy far more interconnected and dynamic than anyone had previously dared to imagine. The chemical signatures detected in 3I/ATLAS had established direct links between stellar nucleosynthesis processes that occurred billions of years ago and the formation of worlds that might be condensing from protoplanetary disks around distant stars at this very moment, revealing the cosmos as a single vast system where every atom had its own biography spanning space and time on scales that transform the meaning of connection itself. And so, tonight, as you drift toward dreams beneath the same stars that witness this cosmic dance, remember that you too are part of this grand tapestry, made of elements forged in stellar furnaces and distributed by processes like those we observed in our interstellar visitor. Somewhere in the darkness between worlds, the fragments of 3I/ATLAS continue their journey, carrying within their ancient hearts the secrets of creation itself, while new wanderers approach from the cosmic deep, each with its own story to tell of the magnificent interconnected universe we call home. Sweet dreams, fellow travelers, and may your rest be filled with visions of distant suns and the gentle music of worlds in motion, forever dancing through the star-scattered night. The gentle whisper of solar wind carries these fragments ever outward, each piece now a chapter in a story that began before Earth learned to breathe. As we watch through our telescopes, tracking their slow recession into the outer darkness, we witness something profound. the birth of galactic memory itself. These wandering pieces of 3I/ATLAS have become living libraries, their surfaces etched with the chemical signatures of two stellar systems, their interiors preserving the original fingerprints of alien world-building, while their outer layers bear the fresh scars of solar transformation. The magnetic fields surrounding each fragment tell tales of their violent birth during those spectacular outbursts near perihelion. Even now, months after the Great Disruption, sensitive instruments detect the fading electromagnetic echoes of that cosmic drama. The charged particles trapped within these diminishing field lines continue their spiral dance, creating radio whispers that grow fainter with each passing day, but still carry information about processes that occurred in the heart of our solar system's most extraordinary visitor. What fascinates astronomers most deeply is how each fragment has developed its own personality during the journey outward. Some pieces, rich in water ice, continue gentle outgassing that creates gossamer trails visible only to the most sensitive cameras. Others, dominated by rocky material and exotic organics, remain stubbornly silent, their surfaces darkening as volatile compounds sublime away to leave behind protective crusts that will shield their interiors during the eons of travel ahead. The isotopic signatures preserved within these fragments represent something unprecedented in the annals of astronomy. Direct samples of stellar nucleosynthesis from another star system, now modified by interaction with our own sun's radiation and magnetic field. Each piece carries within its crystalline structure a record of nuclear processes that occurred in stellar cores light years away and billions of years ago, while simultaneously bearing the fresh imprint of solar wind bombardment and thermal cycling that occurred within our own cosmic neighborhood. The gravitational ballet between fragments creates scenarios that will play out over millions of years as some pieces gradually separate while others remain loosely bound in gravitational families. Computer simulations suggest that several fragment clusters will maintain their association for geological ages, creating mini-swarms of interstellar debris that will eventually encounter other stellar systems as coherent groups, potentially seeding multiple worlds with related materials that preserve the chemical signature of both their birth system and their transformative passage through ours. The dust trails stretching behind these departing fragments paint gossamer highways across the solar system, each stream carrying particles with unique compositions that reflect the specific conditions under which that particular piece was disrupted. Some trails are rich in crystalline silicates that formed under high-temperature conditions during the violent outbursts, while others contain fluffy aggregates of organic compounds and water ice that preserved more gentle formation processes. These debris streams will gradually spread and diffuse under planetary gravitational influences, eventually creating a subtle but permanent enhancement to our solar system's dust environment. The radio emissions from the fragment field continue to evolve in ways that surprise researchers. As particle densities decline and magnetic fields weaken, new types of electromagnetic phenomena emerge that were masked during the intense activity near perihelion. Low-frequency radio waves generated by the interaction between fragment magnetospheres and the solar wind create signals that can be detected by sensitive receivers throughout the solar system, providing ongoing information about plasma physics processes in environments that exist nowhere else in nature. The chemical evolution continues within the expanding gas clouds surrounding individual fragments, driven by reactions between molecular species that were brought together during the disruption process. Solar ultraviolet radiation catalyzes the formation of complex organic compounds that exist transiently in the low-density environment before being destroyed by further photochemical processing. These reaction networks create a kind of interstellar chemistry laboratory that provides insights into the pathways through which simple molecules might evolve into more complex structures during the long journey between stellar systems. The thermal properties of different fragments reveal internal structures that tell stories of their formation within the original nucleus. Dense rocky pieces cool slowly and retain heat for months, while fluffy, ice-rich assemblages reach equilibrium with the cosmic background temperature within weeks. These cooling curves provide information about thermal conductivity and heat capacity that constrains models of how cometary nuclei form and evolve within the cold outer regions of planetary systems. The wake structures created by individual fragments in the solar wind show evidence of complex fluid dynamics processes that operate under conditions of extremely low density and high magnetic field strength. The interaction between outflowing gas from fragment surfaces and the ambient interplanetary medium creates bow shocks and magnetic field draping effects that generate particle acceleration regions detectable by cosmic ray monitors throughout the solar system. The spectroscopic signatures of different fragments continue to diverge as surface materials are preferentially removed by continued sublimation and solar wind sputtering. This natural fractionation process creates chemical fingerprints that will allow future astronomers to identify 3I/ATLAS family members even after they have dispersed throughout the galaxy and undergone further modification during encounters with other stellar systems. The polarization properties of sunlight scattered by fragment dust clouds provide ongoing information about particle size distributions and optical properties that reflect the microscopic processes governing surface erosion and material transport. The measurements reveal systematic differences between fragments that originated from different regions within the original nucleus, creating a kind of archaeological map that reconstructs the three-dimensional structure that existed before disruption began. The gravitational perturbations caused by planetary encounters begin to separate fragment trajectories in ways that will determine their ultimate destinations among the stars. Some pieces follow paths that will carry them toward the galactic center, while others are deflected toward the outer spiral arms where different stellar populations and chemical environments await their arrival. The range of outcomes demonstrates how single events in one stellar system can eventually influence conditions throughout vast regions of the galaxy. The amateur astronomy community continues to track the brighter fragments using modest equipment, contributing observations that complement professional monitoring programs. These citizen science efforts provide temporal coverage and sky area surveillance that would be impossible for major observatories to achieve, demonstrating the value of distributed observational networks in studying transient phenomena that evolve over extended timescales. The educational impact of the 3I/ATLAS mission has transformed how students and the general public think about the solar system's place within the broader galactic community. The realization that our cosmic neighborhood regularly receives visitors from other stellar systems and presumably sends its own messengers to distant worlds has created new perspectives on planetary system evolution and the potential for material exchange on galactic scales. The theoretical frameworks developed to understand 3I/ATLAS behavior have begun to influence models of how interstellar objects might transport not just chemical information, but potentially biological materials between stellar systems. The discovery that fragments can survive disruption while retaining complex organic compounds raises intriguing questions about natural panspermia mechanisms and the possibility that life itself might spread between worlds through processes similar to those observed during the comet's solar encounter. The technological innovations stimulated by the need to coordinate real-time observations of rapidly evolving phenomena have established new paradigms for responsive astronomy that can adapt observing strategies as targets change their behavior. These advances will prove valuable for future studies of supernovae, stellar explosions, and other transient events that require immediate response to maximize scientific return. The data archives created by the global 3I/ATLAS campaign represent an unprecedented resource for investigating interstellar object physics and the processes that govern material transport between stellar systems. The comprehensive multi-wavelength coverage and extended temporal baseline provide a foundation for research programs that will continue for decades as new analysis techniques are developed and theoretical understanding evolves. The philosophical implications of witnessing detailed interactions between our solar system and materials from other worlds touch on fundamental questions about cosmic evolution and the mechanisms through which complexity emerges from simpler initial conditions. The chemical and physical transformations observed in 3I/ATLAS demonstrate how encounters between different stellar environments can create new possibilities for molecular evolution and structural organization that might not arise within isolated systems. The magnetic field measurements conducted throughout the fragment field's evolution have revealed previously unknown aspects of plasma physics in environments where multiple outgassing sources create complex current systems and particle acceleration regions. These observations provide insights into similar processes that might occur in other astronomical contexts, where magnetic fields interact with tenuous but structured gas distributions. The dust grain analysis has shown that materials processed by billion-year exposure to cosmic radiation develop optical and chemical properties that differ significantly from freshly formed particles. This space weathering creates distinctive signatures that can be used to identify interstellar materials within meteorite populations and planetary ring systems, providing new tools for studying the history of material exchange between stellar environments. The isotopic evolution observed in different fragments as they cool and undergo continued outgassing reveals how stellar nucleosynthesis products are further modified by exposure to interstellar conditions and subsequent processing within planetary system environments. These measurements provide direct constraints on galactic chemical evolution models and the timescales over which stellar debris is mixed and redistributed throughout the galaxy. The wake dynamic studies have shown how objects moving through the solar wind at high velocity create disturbances that propagate both upstream and downstream from their position, influencing space weather conditions across volumes much larger than the objects themselves. These effects demonstrate how interstellar visitors can create temporary modifications to the entire heliospheric environment during their passage through planetary systems. The coordination challenges overcome during the 3I/ATLAS campaign have established new protocols for international scientific collaboration that maximize the return from limited observational resources while ensuring that critical measurements are obtained despite equipment failures and adverse weather conditions. These organizational innovations will prove valuable for future multi-institutional research projects that require real-time coordination across multiple time zones and technical platforms. As the fragments of 3I/ATLAS continue their gradual fade into the cosmic background, they carry with them not just the physical record of their remarkable solar encounter, but also the inspiration they have provided to a generation of scientists and students who witnessed firsthand the dynamic nature of our galactic neighborhood. The comet's transformation from mysterious visitor to dispersed family of interstellar messengers has demonstrated that the universe operates as an interconnected system where events in one location can influence conditions across vast distances and timescales. The gentle recession of these ancient wanderers back toward the star-scattered deep marks not an ending, but a beginning, as humanity's understanding of cosmic processes expands to encompass the reality of material exchange between worlds on scales that transform our conception of planetary system evolution and our place within the grand community of stellar civilizations that populate the galaxy. And so, as these fragments carry their precious cargo of information back toward the interstellar night, they remind us that we too are part of this cosmic conversation, citizens of a universe where boundaries dissolve and connections form across the vastest reaches of space and time, forever linking world to world in the eternal dance of creation that unfolds beneath the gentle light of distant suns. Each one a beacon calling across the darkness to tell us that we are never truly alone among the stars. And so we reach the gentle end of our cosmic journey, dear listeners, having followed 3I/ATLAS from its first faint glimmer in Chilean telescopes to its spectacular transformation into a family of interstellar messengers now fading back toward the star-scattered deep. We've witnessed something extraordinary together, the collision between worlds separated by light years and eons, a dance of plasma and ancient ice that revealed the galaxy as far more connected and alive than we ever dared imagine. Through coronal mass ejections and chemical signatures, through disruption and dispersal, we've seen how a single visitor from another star carried within its frozen heart the entire history of galactic evolution. Each molecule a tiny time capsule, preserving memories of stellar furnaces that burned and died long before our sun was born. The fragments now departing our solar system take with them not just their alien chemistry, but also the fresh imprint of their encounter with our own star, creating cosmic correspondence between stellar systems across the vast reaches of space. Perhaps most remarkably, 3I/ATLAS has shown us that we live in a universe where nothing truly ends, where every atom has its own epic biography, where the boundaries between here and there, then and now, dissolve into a single magnificent tapestry of connection and change. As you drift towards sleep tonight, remember that you too are woven from stardust that once wandered between worlds, that the very elements in your breath have traveled unimaginable distances to find their way to this quiet moment. Somewhere in the darkness beyond Neptune, the fragments of our interstellar visitor continue their patient journey, carrying secrets between the stars while new wanderers approach from the cosmic deep, each with stories yet untold. The universe whispers its mysteries in the language of light and motion, in the gentle warming of ancient ice and the slow dance of gravity across the void. Sweet dreams, fellow travelers, and may you rest peacefully, knowing that we are all part of this cosmic conversation, forever connected to distant suns and alien worlds through the endless beautiful exchange of matter and energy that makes us citizens not just of Earth, but of the galaxy itself. Earth, but of the galaxy itself.